So 4.2 will be all about Euler's number. What is Euler's number? You guys have probably seen it before. You guys have probably used it in class already. You just haven't been told what it's called. So as always, I'm going to try to talk about where it came from. If you're not too particularly interested, I don't know, fast forward through to the examples. You do whatever you want to do. But the idea is that yesterday, we saw one application of exponential models that was specifically finance, compound interest, coming up with money, etc., etc. Now, after doing the practice, I hope you guys notice one important idea from yesterday. With all things equal, the more compounds you have, the greater the amount. And what I mean by with all things equal is if you have two bank accounts with the same principal, same interest rate, same time, everything's the same, but the only thing that's different is the number of compounds, well, the account with the bigger amount of compounds will have a greater amount of money at the end. So here's the question that we sort of want to talk about today. How high can I crank up these returns? How high can I crank up the amount of money? Just to make the math simple, I don't want to be dealing with thousands of dollars because why fantasize about something I'm never going to have? Let's suppose we invested $1, right? So suppose we invested $1, make the numbers easy, and let's just pretend that we want to get as much money as possible. So there's a crazy bank out there that'll give us 100% interest rate, which is also 1. That's why I chose it to make the math easy. How is, that's the biggest amount I can get if I crank up all of these compounds. So to answer this question, let's just make a quick chart. Let's recall the formula, though, just so you don't have to flip back into your notes. The compound interest formula is A equals P times 1 plus R over N to the NT power. So let's see what's going on here. Now, I don't want to deal with 2 years, 5 years, 10 years just to make the math simple. Let's assume that T is for 1 year. I just want to figure out what's the biggest amount of money I can make after 1 year. So let's organize our information to a table. Let's do an N by this table here. So let's see, if we plug in all of our numbers, P is 1, R is 1, and T is 1, so that gives us what? 1 plus 1 over N to the N. That's all we're interested in. 1 plus 1 over N to the nth power. So let's do 1 compounds. I want to see what happens when I crank up the number of compounds. Let's do 10. Let's go crazy. 50 compounds in a year. 100 compounds in a year. What about 1,000 compounds in a year? What about 100,000 compounds in a year? What about 1,000,000 compounds in a year? Right? We saw yesterday daily 365 compounds sure gave us a lot more money than 1 compound a year. So 1,000,000 compound a year should be insanely big, right? Well, so we'll go ahead and just take all these N values and plug them into this formula here. So I'm not going to waste your time. If you want to save the fun for yourself, you can pause the video and figure out for yourself. But if you were to take these N values and plug them in one at a time into this formula, this is what we should get. When we plug in a 1, you get a 2. When you plug in a 10, you get a 2.593744246. When you plug in a 50, you're going to get a 2.691588029. When you plug in 100, you get a 2.7048133829. So, yes, look at these numbers. They're getting bigger and bigger and bigger. I'm getting a lot more money than a regular $2, right? What if I crank it up to 1,000? That's 2.71 6,923,932, 100,000, 2.718268237, a million, 2.718280469. Gee, those last three really didn't matter much. I mean, if you look at the first four, went from $2 to $2.50, $2.69, $2.70. I mean, it got bigger and bigger and bigger. I mean, we got more money, but it looks like as we keep compounding, the change is sort of negligible. It doesn't really seem to increase much, right? So although the total amount does increase as the number of compound increases, there seems to be a maximum, or there seems to be a limit to the amount that I can actually get. Right? So although value increases, there seems to be a maximum or limit we can get. And that's the idea. This limit amount, we define this as the constant E. That is what the number E is, and this is what we call Euler's number, 2.7182881 blah 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 blah. I haven't have it memorized. Some people like to memorize pi. I'm pretty sure there's some people that like to memorize E. I certainly do not. Okay. So that's all E is. E is sort of like this maximum growth rate that you could ever have. I mean, we had ideal situations, 100% growth. No one's ever going to give you 100% growth. Maximum compound. You're compounding every single split second, every single moment, but we still seem to be limited in the amount of money we can get, $2.71. 72 if you round up. So that's all. That's the big reveal. That's the big secret. Although it's a pretty neat idea that E is this inherent attribute to all exponential functions, what we can do with it is just what we can do with regular exponential functions. So this lesson, 4.2, you'll be doing the same stuff that you did in 4.1. We did some graphing in 4.1, so we're going to do that again. We did some interest problem. We're going to do that again in 4.2 here. But we do sort of have a situation here. Recall that any function of the form f of x equals b to the x may be called an exponential function. Of course, b has to be positive, not 0. Right. Well, we can put any base you want. Heck, you can use base pi if you want, base 3.8, whatever number you want. We just have a special vocabulary if the base so happens to be the special number e. If the exponential base is e, we call f of x equals e to the x the natural exponential function. Or, for you Ohio State fans, the exponential function. If I can spell, exponential function, right? So anything can be an exponential function, but specifically if you're using a base e, we call it the natural exponential function or simply the exponential function, right? Well, what some of the stuff I'm expecting you guys to do today for this lesson? Well, just what we did for 4.1. I expect you to be able to graph, and I expect you to be able to do compound interest. Well, the problem with graphing is we had two types of graphs. We had an exponential growth function. We had an exponential decay function. Those are the two types of exponential functions that we can sketch. And what determined what type of function you had was the base. But if the base is e, and e is always 2.71828 blah, 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 how in the world are we ever going to get decay functions? Well, you have to look at the exponents of e themselves. So you'll have growth functions if your exponent of e is just a regular x, and you'll have decay functions if it's negative x. So that's all you have to worry about. Everything else is the same. Function transformation, shifting up, shifting down, left, right. It's all the same concepts as 4.1. So let's do a couple of quick examples here. Suppose I ask you to sketch f of x equals 3e to the negative x plus 1 minus 4. So the first thing we have to do is read all the transformations. So if we forgot what the transformations are, again, please refer back to your 4.1 notes or rewrite them again, because writing them over and over and over will help you remember. A minus 4, this says down 4. A plus 1 with the x says left 1. Now this negative here would normally tell us a flip across the y-axis, but since we're dealing with the natural exponential function, all this simply means is we'll have a decay function. And of course, we have a vertical scale by 3. Those are all the transformations that are present. So when it comes time to sketching, just follow the transformations. And remember, we do the scaling, the multiplying before we do the left, right, up, down. What transformations do you need to do? At least for me, I'm not going to expect you to spend 5 minutes making an XY table. Just go ahead and transform the special point 0, 1, and go ahead and transform the horizontal asymptotes. E, the natural exponential function, follows the same rules. So here we go. Every single exponential function starts here, 0, 1. He gets scaled by 3, so 1 times 3 would move him up to 3. Then you're going to go left 1, and then you're going to go down 4. 1, 2, 3, 4, right there. So that should be the new special point. Next, you have to move the horizontal asymptotes. And remember, the horizontal asymptote is only affected by up and down motions. He's not affected by scales. It's not affected by left or right. It's affected by vertical translations. So all horizontal asymptotes starts at y equals 0. Since it said go down 4, I'm going to move him down 1, 2, 3, 4. There is our new horizontal asymptote. And then all you got to do is sketch the shape. Since we know it's a decay function, decay shape should be something that looks like that. So just draw that shape through your special point, and then that's all I'm looking for. Easy peasy. I suppose I have time to do one more. F of x equals negative e to the x minus 1 minus 2. So first thing I want to do, and I'm going to sketch him. Guess the instructions would be good. First thing I want to do is read all the transformations. So here is a down 2. Here is a right 1. The positive x tells me it's a growth function. And the negative from the e is a flip over the x-axis. So hopefully by now we're getting more comfortable with reading transformations, because if you can read transformations, you can easily sketch, as long as you know what parts you need to sketch or transform. So let's go ahead and make a coordinate system really quickly here. Undo. There we go. For exponential functions, you're always transforming this point here, 0, 1. So listen to your instructions. Remember, we always do multiplication transformations before we do add and subtract transformations. So we actually have to do this flip part first. So if I flip him over the x-axis, this point goes to here. So that point will go to here. Then I need to do right 1. So he'll go to here. And then I need to go down 2. 1, 2. He will go down there. That is our new special point. Then you go ahead and move your horizontal asymptote. It always starts at y equals 0. He is only affected by up and down motions, not scaling, not flipping or anything. So I only have down 2. So we're going to move down 1, down 2. That is our new horizontal asymptote. Now all I need to do is do my shape. It was a growth function. So the growth shape should be something like this, but it got flipped. So you just have to do it upside down, something like that. It got flipped upside down. So just go ahead and draw your shape through that special point in that manner. Easy peasy. So that's one thing you're going to be doing in this practice is sketching, which we did in 4.1. The other thing you're going to have to do is compound interest. Now, how does compound interest work when it comes to E? Well, remember that E is sort of the hypothetical constant growth at every single time. What if you're constantly getting, like every split second you think of, you're getting interest? Well, that can be applied to our compound interest formula, and it will change our compound interest formula just slightly. Now, this will be the one point where I'm going to go, you know what? I'm just going to give you the formula. If you are really interested in seeing where it comes from, please ask me after class or after this video, and I'll gladly tell you. But it's something that you'll talk about in calculus. But you can actually do it in pre-calculus. But for right now, I'll just go ahead and give you the definition. So I'm going to skip the derivation. If you're truly interested in where this formula comes from, please, please, please talk to me. So this is called continuously compounded interest. Right? That's the trigger word there. If you see continuously compound, don't use the old formula. You're going to be using the new formula. Continuously compound interest is calculated by A equals P E raised the RT power. And all the pieces are the same as compound interest. A is the final amount or the total amount. P is the principal, which is the initial amount. R is your rate as a decimal, and time is years. Now you only use this formula, again, if you read the word continuously. If it's just regular, semi-annual, quarterly, whatever, you're going to use the regular compound interest formula that we talked about yesterday. So let's take a look at an example. Find the amount after 3 years if $1,000 is invested at a rate of 12% per year, compounded, ... This will be a multi-part question. A, daily. B, continuously. So just like yesterday, when it comes to this interest problem, all you have to do is just read the story and figure out what letters they give you. So let's start at the beginning. Find the amount after 3 years. Well, that's clearly my time. If $1,000 is invested, so the $1,000 is what we invested, that's our principal, at a rate of 12% per year. Well, that's easy. That's my R, rate. Per year, compounded daily. So the word daily means the number of compound is 365. And continuously, that's the trigger word for the E formula. So to do part A, because it's a regular compound, we go back to the old school formula. A equals P times 1 plus R over N to the NT power. And we just plug every single bit that they give us. They give us 1,000 for P. They give us 0.12 for R. They give us 365 for N. And then they give us 3 for time. Pop that into your calculator, you're going to get about $1,433.24. For part B, though, since they use the phrase continuously compound, we're going to use this new formula. A equals P, E raised to the RT power. But it's still just plugging in the pieces that they give you. 1,000 was my principal. E is just a number. The rate is a 0.12, and the time is a 3. Go ahead and use your calculator. E is just a button on your calculator, and you're going to get about $1,433.33. So, I mean, it's not significant amount more money, but you can see it is more money nonetheless. And of course, daily is really close to continuous, because although continuous is every single waking moment, I don't think I've ever met any bank that gave you daily interest. That'd be a lot of money for you. So that's it. That is 4.2. Although E is this mystical, wonderful number that has many applications in the world of mathematics, it is just a number nonetheless. So don't get intimidated by it. It's the same thing as 4.1. It's just we're using this new number called Euler's number. Good luck.